Hello everyone, my name is Fei Wang, I'm EV R&D manager from Saint-Gobain Tape Solutions. Today I'm going to talk about multifunctional material solutions to optimize cell performance and pack design. Saint-Gobain is a strong global group. Innovation is in our DNA. We have 8 R&D centers in America, Europe, and Asia. We also have a global manufacturing footprint in order to provide agile support to our local customers. Tape Solutions is a business unit within Saint-Gobain. Its specialty tape and foams provide bonding protection and insulation functions for demanding applications. Over the years, we developed multiple materials for battery pack applications, including at cell level mechanical cushioning and thermal runaway protection, and also at module and pack level thermal interface material, gasket, and mechanical holding pad. Heavy-duty vehicles need very robust battery packs. These type of vehicles have very heavy battery usage because it has long annual mileage. The batteries are most of the time in use. Hence, the durability of this type of batteries are very important. In the meantime, thermal runaway safety is still essential for all kinds of vehicles. In this presentation, we are going to share with you our recent development for normal usage to prolong battery's lifetime through mechanical cushioning, and also the progress for thermal runaway protection. Optimal compression level is critical for battery's longevity. During charge-discharge cycle, a battery is changing its dimension, including reversible breathing during each charge-discharge cycle and irreversible swelling throughout a battery's life. Research has shown that the proper, not too high, not too low level of pressure is critical to maintain the capacity for a pouch cell system. And our recent study has proven that this rule applies to prismatic cell system, although at a different pressure level from pouch cell. In fact, different batteries need different mechanical management solutions. The deciding factor include cathode, anode, electrolyte chemistry, as well as case material and design. The upper right curve is an indication of different compression curve that is requested by pouch, prismatic, and solid-state batteries. Our polyurethane and silicone technology allow us to customize our compression curve for your battery's needs. In addition to tunability, we emphasize the durability of our product as well as the capability to support our customers' design process. I'm going to use 2 case studies to illustrate. My first case study is to evaluate the durability of cell-to-cell compression foams. We utilize a fatigue machine with environmental chamber to test that property. Subjecting the material at room temperature 60 C and -20 C, we are mimicking the material's behavior in normal climate, very hot climate, and very cold climates. And we are subjecting material to 3,000 cycles, representing a battery pack's typical duration. As can be seen from this slide, Norseal PF 27250 product at cycle 1, 100, 1000, and 3000 has a very similar compression curves. And the SEM image on the right also indicate a very minimum change before and after 3000 cycles. When being exposed to high and low temperatures, Norseal PF27 250 product is demonstrating very stable mechanical cushionings. As you can see from the left picture, the compression curve at room temperature 60 C and minus 20 degrees C are very similar to each other. In contrast, other PU foam could soften significantly at 60 C hot climates, or could stiffen significantly at a minus 20 C cold climate. And this contrast indicates if not properly chosen, the compression foam could provide the battery pack quite different mechanical cushioning under different temperature, hence influencing the battery's life. Our second case study illustrates how we use modeling to support customers' designs. We developed a digital tool for compression pad that can select the proper compression pad or compression pads combination to meet customers' design needs. The bottom pictures shows an example of how we choose two foams to meet a special requirement from a customer's battery's need. In addition to material selection, we also consider our products' different properties in different usage stage. For example, because of its viscoelastic properties, foam typically exhibit different mechanical property during the fast assembly process as compared with the slower breathing and swelling process during the cell charge-discharge. And our tool can quantify this phenomenon for our customers. An example is on the right figure, and the solid lines represent the quantitative testing in the instrument machine, while the dotted lines are for the mechanical simulation. And you can see they overlap with each other pretty well. And we're able to provide all this material to support our customers' design process and make sure that it's realistic in their actual assembly and testing process. Regarding thermal runaway propagation protection, two product families are popular in today's design space. One is inorganic insulation, such as aerogel or inorganic fiber mat. They typically have very good thermal insulation. However, because of their intrinsic mechanical property, the durability through thousands of cycles is typically inadequate. And the second material family is organic insulations, such as silicone or polyurethane foams. And they enjoy very good mechanical durability. However, because of the natural degradation at thermal runaway temperature, this organic insulation will lose its capability. And today we are proposing a new solution with good normal usage mechanical cushioning over thousands of cycles, and also sufficient thermal insulation at thermal runaway temperature. To ensure the robustness of our design, we not only test our material in lab at a high temperature, high compression, real battery testing, we also utilize model-assisted design to simulate this thermal runaway process. The pictures on the left-hand side of this slide indicate a typical short stack testing of prismatic NMC 811 cells. The reference foam mica laminate insulation was not able to stop the propagation. And in fact, we found after a forensic study that not only the thermal conductivity at room temperature is important, but also the thermal conductivity at thermal runaway temperature, as well as the integrity of the foam at thermal runaway temperature are critical for this protection. We developed a new foam material with significantly lower thermal conductivity and a much higher structural integrity at thermal runaway temperature. The before and after thermal runaway picture of this new foam is shown in the left pictures. And as expected, this new foam stopped the propagation between cell 1 and cell 2 in the same 4-cell stack test as shown in the previous slide. In conclusion, we support our customers' success with a wide range of robust and durable solutions. With our comprehensive testing, simulation, and real-life validation capabilities, as well as broad experience in various battery types and industrial automation process. We are honored to be selected by APA-E Circular Program to continue our journey to extend the battery's lifetime and ensure safety with our packaging materials. If you have further questions, please feel free to reach out to us.